Okay, so now we're going to go over boundary layers. And I'm going to call those BLs. And why they're important is because potential flow, which we didn't go over in this class, but it's based on inviscid flow theory. So potential and other flow theories are useful to find pressure drag. And you do this in aero. So, but to get the skin friction, or even understand the influence of viscosity on the flow field, you need a different theory. Okay, and now in the early 1900s, Pronto introduced the concept of a boundary layer. Okay, because back in the day, you couldn't solve the full Navier-Stokes equations with viscosity. And even today, it requires fairly large computers to do a lot of practical cases. And from experiments, he recognized that regions where viscosity is important, again, this is for high RE flows, is just close to the object. Okay, so the only region where viscosity is important is close to the object. Okay, and further away, the flow is inviscid. Okay, so if I scroll up back to the cylinders, up to this one here, well, this little region here, there's a very thin region here in green, and in front of the cylinder, and that region is called a boundary layer, and it is very thin relative to the diameter of the cylinder, and only in this region here, at least for the front of the cylinder, is where you need to consider viscosity. Everywhere else outside of it, the flow is inviscid. And in this type of flow outside of it, where the flow is inviscid, actually it's called a potential flow, and it's irrotational, and Bernoulli is valid outside. Okay, and so in this inviscid region, you can use Bernoulli everywhere. You don't need to follow streamlines like you do in the other case. But again, in aerodynamics, you guys they cover that in a lot more detail. We just basically discuss it, and that's about it. Okay. And so if we consider the canonical example of a boundary layer, and that is of a flat plate. Okay, and so we have a flat plate. Oops, wrong marker. So this is a flat plate. Okay, and we have flow of some free stream velocity cap u interacting with this. Okay, well, what Prandtl observed experimentally is that the velocity profiles would look something like this, where it would essentially be at u above a certain, oops, wrong thing, that the velocity profile would be essentially constant in u above a certain height, and in this region here is affected by viscosity, where remember that when when a fluid interacts with a solid wall and viscosity, and it's a viscous fluid, the no slip condition holds, so the velocity of the fluid is 0 at the wall of the flat plate, so the fluid has to stop. Okay, and then this produces a layer of stopped fluid here, but then the next layer of fluid above it sees a layer of stopped fluid, and so that introduces a shear stress, which then slows down the next layer, and this effect keeps progressing until the velocity reaches the free stream velocity. And as he went further out, Prandtl noticed that this region got thicker. Oops, and I'm drawing it with a different U, but this is the same cap U. Okay, and so the velocity profiles look something like this. And what he noticed was that this height here, and this is about where, and I'll just call this this velocity profile in here U, is where U is about equal to 95% of the free stream velocity. Is he noticed that this region here, which that height he called delta, is actually very, very thin, and this is where, and in this region here is where viscous effects are important. Okay, and so this region in here is called a boundary layer. Okay, and in this boundary layer is the region where viscous effects are important. So if I use the same highlighter that I did last time to basically indicate where the viscous effects are important, it would be in this region only. Okay, and so viscous effects are important in there, and what he noticed is, and we would define X, is that that delta is a function of X. That is, the height of this boundary layer increases as a function of distance along the plate, and Prandtl observed importantly that delta over some free stream distance L, and I'll just call this some distance L, is much, much less than 1. So that is the height of the height of this boundary layer is very small compared to the axial compared to the x distance along the flat plate. Okay, and so this would be the plate length. Okay, and this delta is called the boundary layer height. And it is, if I define y, oops, wrong way, sorry about that. If I define y, it is, delta is where is the y, where u equals 99% of cap u, as I said above, or you'll sometimes commonly see 95% of u. There's no, once you understand boundary layer theory, there's no really super precise definition of when you get above the boundary layer or when you are inside of it. Okay, it's just when it is close enough. It is when it's when the velocity profile here is close enough to the free stream velocity. And a characteristic of a boundary layer is that, oops, I keep hitting the wrong button. Is that in the boundary layer there's a very sharp velocity gradient near the wall of the flat plate, and as you go above, and then as you reach the top of the boundary layer, again, I'm not the best drawer in the world, but it's actually perfectly flat, and there is no, and because du dy equals 0 above the boundary layer here, if it's a flat plate, there is no viscous stress. So the region above the boundary layer is inviscid, and that is not because the viscosity is 0. The viscosity is a physical property. It is never not 0, except for very special fluids. It's actually superfluids. And so it is not inviscid because the viscosity is 0. It is inviscid, at least in this flat plate configuration, because there is no velocity gradient. And if you recall from viscous stress, there is no shear stress if the velocity gradient is 0. Okay? And so there are some consequences to Prandtl's observation. So if delta over some characteristic length is very small, then in a graduate level class, you can work with the Navier-Stokes equations and non-dimensionalize them and apply this assumption here, and just the mathematical consequences of that assumption, and just working through to the end, you can actually derive the full boundary layer equations with this one assumption here, is that the region where viscosity is important is very, very thin, very thin with respect to the x distance. Again, that's really the one assumption that Prandtl makes, and then he just worked through the Navier-Stokes equations, and then basically did it, and basically followed through with the mathematical consequences of this assumption here. And we're not going to do that in this class. You guys will probably be pretty happy about that. But this greatly simplifies the Navier-Stokes equations. And it simplified them to the point where even 100 years ago, where they didn't have computers, or where a computer was a poor graduate student iterating, basically doing computational fluid dynamics by hand, was simply not practical to solve. And so this boundary layer theory greatly simplified the Navier-Stokes equations. And as a consequence of this, viscous effects are only important if y is, oops, forgot the y, if the vertical height above the plate is less than the height of the boundary layer. Okay, and 3, at least for the flat plate, the x component of the velocity equals the free stream velocity if y is greater than or equal to delta. Okay? And a consequence, if you work through the Navier-Stokes equations, you find that partial p, partial y, equals 0 in the boundary layer. Okay, and so if I draw a little flat plate here, and then the boundary layer, that is at any x location, the pressure is uniform in y. Okay, and so this is P as a function of x. And in this strip, the pressure is, the pressure is not equal to a function of y at in the boundary layer. Okay, so that is the pressure in this entire strip is not a function of y, so that the pressure at the plate is the same as the pressure on top of the boundary layer. Okay, and now the pressure might be different here, but at least in a vertical strip, the pressure will be perfectly uniform. Okay, and so this has the consequence that the pressure is imposed on a boundary layer by the inviscid flow above it. Okay, and so that means is that you can apply inviscid flow theory, even Bernoulli, to find the pressure as a function of x, and then that pressure as a function of x will be the pressure as a function of x in the boundary layer. Okay, and so that greatly simplifies things. Okay, and also you could sort of view this as the pressure is basically squashing down on top of the boundary layer. And also in aerodynamics, if some of you choose to take that, you will learn inviscid flow theories where you can actually find this pressure as a function of x. Okay. Now, the thing about the boundary layer is that, as I said before, is that there's no slip condition at the surface of the flat plate. And that produces what's called a velocity deficit. So if I draw another flat plate and the boundary layer, there is a region here where the flat plate slowed the velocity down, which is right here. And so if I were to extend this u straight on down and then shade this region here is called the velocity deficit. Okay, and due to this velocity deficit, the streamlines are actually pushed up pushed up a little bit, and so the streamlines actually they are very gentle, and they are pushed up just a tiny bit. Okay, so the streamlines are slightly pushed up by the boundary layer. Okay, and 6, and this is also related to the velocity deficit, is that there's another characteristic. It's called the displacement thickness. And that is delta star. Okay, and the displacement thickness is, you could imagine that if I have a flat plate and I have the free stream coming in, and I have our boundary layer, and I have the velocity profile of the boundary layer. If I draw a control volume, or if I just draw a dash surface here, and a dash surface here, and I compute if I compute the flow rate through here, which would be the integral from 0, this goes all the way up to infinity u dy. This would be, y, and this would be u of y. And I compute the flow rate through this surface here, which would be the integral of infinity u of y dy. But here, in this location, it has not felt the presence of the boundary layer. So here, it is equal to the free stream. Velocity, and so that's basically constant. And so here it is easy to see that basically this velocity profile here has not felt the presence of the boundary layer, but this portion has. And so if I were to compute the flow rate through basically this fictitious line or plane here, I would get a larger number than the flow rate through this fictitious line or plane here. So now what the displacement thickness is if I pick a vertical distance and call it delta star, and instead of integrating from 0 to infinity, I integrate only, I exclude this region here. So I integrate from delta star to infinity of u dy. And so basically I'm going to define this, delta star such that the volume flow rate through the volume flow rate through this plane here is equal to the entire volume flow rate at a particular x location in the boundary layer. Okay, so I'm going to say that this is equal to the integral from 0 to infinity u dy, and this is in the boundary layer, and this is just outside a boundary layer, or just upstream of the boundary layer. Okay, well, I can play some games. I can play some games with this, and essentially I can play some games with this integral, and I can say that the integral of from delta star to infinity is equal to the integral from 0 to infinity minus, and I should be formal here, of some function dy, let's call that f, is equal to the integral of f dy minus basically the integral of this whole piece here, and we got to subtract out that piece over here, minus the integral from 0 to delta star f dy. Well, I can apply this to u, and then I have the integral of delta star to infinity u dy equals the integral from 0 to infinity of u dy minus the integral of 0 to delta star u dy. Well, the free stream velocity cap u is not equal to a function of y, so I can just yank that out. And so the second little integral here is equal to u times the displacement thickness delta star. Okay, so then we have, I'm going to take this and substitute it into here. Then we have the integral from 0 to infinity, oops, that's a bad infinity, of u dy minus u delta star equals the integral from 0 to infinity of u dy. Okay, and so this implies, again, u is constant, so I can move them in and out of the integrals at will, that the integral from 0 to infinity u dy minus, this is, I gotta be careful with my u's here, cap u dy minus the integral from 0 to infinity a small u dy, where again small u dy is the velocity profile in the boundary layer, equals cap u delta star. Well, these two integrals here have the same bounds, so I can combine them, and then I'll divide both sides. By cap u. Then delta star will equal to the integral from 0 to infinity of 1 minus u over cap u dy. Okay, now this sort of looks nasty because we got to do this integral up to infinity, but in reality we don't, because u of y equals delta, or not equals delta, equals the free stream velocity cap u if y is greater than delta. So what this means is that you can break this integral into two pieces. The integral from 0 to the height of the boundary layer times 1 minus small u over cap u dy plus the integral from delta to infinity of 1 minus u over cap u dy. Oops, I keep hitting that button, sorry about that. But at this location, this is 0 because u equals cap u. Oh, it's kind of neat. Okay, so then delta star, the displacement thickness, equals the integral from 0 to delta 1 minus small u over cap u dy. Okay, and so essentially what delta star represents, if I scroll back up to my diagram, is that represents basically this height here, and this section here, this height is you can think of it as blocked off. It is the free stream. Flow that is blocked off by viscous effects in the boundary layer. So why do we care about the displacement thickness? And how is it used? I mean, why did I spend so much time going over this? Well, it turns out that how it's used is it represents the portion of the flow that is blocked. So let's consider we are going to measure something in a wind tunnel, like the drag on some goofy object or something like that. Okay, and coming into the wind tunnel, we have a constant free stream flow. Now there's a problem here, and that problem is that when the flow comes in, it's going to interact. When the flow comes in, it's going to interact with the upper and lower walls of the wind tunnel. And that's going to produce a boundary layer. You can't get away from that. Okay, and if the boundary layers are huge, what's going to happen is the boundary layers are going to directly interact with the object. But at the very least, what will happen is that the boundary layers will actually accelerate the flow will accelerate the flow. So you could think of, I could define this distance here as delta star. Okay, and so remember, this is the portion of the free stream flow that is basically, this is the portion of the free stream flow that is basically blocked off. And this distance here, if I define the total height here as h, this distance here is h minus 2 delta star. Okay. And so what the boundary layer in effect does, or what the displacement does, is it basically says that basically this portion of the channel is blocked off to the flow. It is basically blocked off to the flow. And so what happens is that it basically restricts the cross-sectional area for the flow, and it acts like an area reduction. So it is acting like a nozzle in this case, in that it is accelerating the flow. Okay? And so this is the area as a function of x is decreasing due to delta star. Okay? And if you think back to conservation of mass, if we assume incompressible flow, if we assume incompressible flow, then U will increase as x increases, basically meaning because the effective flow area is decreasing as a function of distance down the wind tunnel, and the area is going, which means the area is going down, and to keep and to satisfy conservation of mass, that basically means that the free stream velocity accelerates, and basically what that causes, if we draw a little diagram here, this is just some value. At the center line of the channel is that the effective flow area will look something like this. And because of that effective flow area, the flow velocity will accelerate. Okay, and then because of the acceleration, and remember that in the core here, where it has not felt the presence of the boundary layer, it is inviscid, and Bernoulli is valid. Okay, which means, according to Bernoulli, if you increase the velocity, then you have to decrease the pressure. Okay, and so that sort of changes the conditions that the object sees. And experimentalists typically don't want that. So how do they counteract this? Okay, because this is a boundary layer thing, and that flow acceleration is just basically caused by the effective blocking off of a part of the flow by the boundary layer, or restriction of the flow by the boundary layer. So wind tunnels want U of x to be constant. That is, they do not want U to be changing as we go further and further down the streams, but the BL messes that up. So how do they fix? And the answer is, in a lot of cases, or like sometimes they will actually contour the wind tunnel. Okay, and so essentially, if you consider delta star, they define the walls of the wind tunnel such that if they consider the displacement thickness, that h of x, or that the effective area is constant. So this would be h minus 2 delta star. Okay, and so essentially to achieve that, what they have to do is that they have to gradually expand the walls of the wind tunnel and make the height as a function of x. Okay, and so this region here is the region that is blocked off by the displacement thickness, and the effective area is constant. And because the effective area is constant, that means at the core of the channel, which means the very center of it, that means a of x is constant, even though I didn't draw it like that. I think I'll redraw it. A of x is constant, p of x is constant, and u of x is constant. Okay, and so this is often a much more favorable condition in which to run your wind tunnel. Okay, and so this, for a very sensitive measurement, this is actually done. And so basically what they do is they change the geometry of the wind tunnel to accommodate the effective flow restriction by the boundary layers. Okay, and how they do that is they basically change the total cross-section area of the wind tunnel to be twice the displacement thickness at that given location. Okay, and I believe that was 6. That was the long one. Okay, yeah. Sorry about that. So number 7 would be the momentum thickness. It's a similar concept to the displacement thickness, but it's to momentum. And I'm not going to derive that or go over that in much more detail. And that's defined as theta, and that goes from 0 to delta. And that's the integral of small u over capital U times 1 minus small u over capital U dy. And theta is the height that accounts for the deficit in momentum from the free stream. Okay, and it's often used in drag calculations. We're not going to use it in this class, but it's just nice to know that it's there for those of you who do more with fluid mechanics. You will definitely run into the momentum thickness a bit more often. And a consequence of Prandtl deriving the boundary layer theory, assuming that delta is very small, is that boundary layer theory is only valid if delta is much, much smaller than x. And a criteria for if you can use boundary layer theory or not, if the Reynolds number based on distance along the flat plate, which equals cap u times x over the kinematic viscosity, that needs to be greater than or equal to roughly about 1,000. And this implies that it's not BL theory is not valid near the tip. And why is that? Because if I draw, oops, that's a bad flat plate. If I draw the flat plate, and this would be x, and I draw here delta, x in this region here, delta is approximately on par with x. So it is simply too close to the tip, and so basically REX are the Reynolds number based on distance along the flat plate is simply too small for the assumptions inherent to boundary layer theory to be valid. Okay? And what boundary layer theory gives you is it gives you the velocity profile. And after you find the velocity profile, you can find the wall shear stress. And that's a function of x. And it turns out that tau wall is higher near the tip. Okay, and the reason being is you can think of this heuristically is I have a flat plate here and I have a boundary layer. Well, to a certain extent, we know that at any location, say here, here, and here, the velocity here must match the free stream velocity here. But in this region here, that has to occur in a much shorter distance than, say, way over here. So the velocity gradient near the wall in this location here is going to be higher than the velocity gradient in this location over here. So if I just sketch a few cartoony velocity profiles, I don't like that one. There, that one's better. Okay, and then I draw another one over here. And this would be y, and this would be u of y. Okay, here we can see that du dy is higher than over here. Okay, and recall that tau wall equals mu du dy at the wall. Okay, and so this basically means that since the velocity gradient here is smaller because it had a shorter boundary layer theory, or it had a shorter boundary layer in which to transition from the no slip condition, which means the velocity here is 0, to the free stream condition, that had to occur in a much shorter distance than it did over here. And so that means that the shear stress is actually higher over here than it is over here. And if I was to plot, at least qualitatively, the wall shear stress, that would look something like this. And in theory, it's singular at the very tip of the plate. And that just basically means that the boundary layer theory is not accurate near the tip. It's not that the shear stress actually goes off to infinity. Okay? And so then for a laminar boundary layer, Okay, and for a laminar boundary layer, I'll call that LBL, and that's from Prandtl, and his student Blasius was the one who actually solved the equations through what's called a similarity solution. You guys will have some experience with that in heat transfer. Okay, they find that delta over x equals 5 over the square root of Reynolds number based on distance along the flat plate. And delta here, they defined it as the height where u over the free stream velocity equals 0.99. And Rex is defined as rho u times x over mu, or if you prefer, u x over the kinematic viscosity. Okay, and now how Prandtl obtained that was that this boundary layer theory gives the velocity profile. Okay, so if you have the velocity profile and you want to know how high the boundary layer is, you just need to ask it, well, where is u in the velocity profile equal to 99% of the free stream velocity? So after you have the velocity profile, you can find all of these things. And delta star over the length equals 1.721 over square root of Rex. The momentum thickness divided by x is equal to 0.664 divided by square root of Rex. The wall shear stress equals 0.332 u to the 3/2 power. Again, I'm just writing these results down. Times the square root of rho mu over x. And the skin friction coefficient, which is defined as the wall shear stress over the dynamic pressure in the free stream, that's equal to 0.644 over the square root of the Reynolds number based on x. Okay, and this is called the skin friction coefficient. Okay. And again, these are for laminar boundary layers, all of these results here. And now one thing to note about the heights of the boundary layers is if you evaluate them in terms of x, is that the deltas increase with x to the 1/2 of power. Okay, so not that fast. Okay. And then finally, for the flat plate, we can find the drag coefficient and the net drag force. So using tau wall, you can find the net drag force on a plate of length L and width, we'll just call that W. You can find the net drag force on this flat plate by basically integrating the wall shear stress. So that would be the integral from 0 to x, tau wall dx, times, assuming that the boundary layer is the same at this position as it is the same on basically this depth here. You can just multiply that by W, and if you do that, that's what the drag is equal to. Then the drag is equal to the width times 0.664 times u to the 3/2 times square root of rho mu times x. Now note, W is usually unit depth. So drag is usually reported at least drag for a flat plate is usually reported as the drag is equal to 0.664 times the free stream velocity raised to the 3/2 power times square root of rho times the viscosity times x, and this is understood to be unit depth. Okay. And then the drag coefficient for the strip, or for the flat plate, D is equal to D divided by the dynamic pressure, basically rho u squared, times A, and this is actually the planform area. It's an infinitely, these flat plates are assumed to be infinitely thin, so a frontal area makes absolutely 0 sense. And so if you stick in the numbers, this will be CD is equal to 1.328 over square root of REL, where REL equals rho times the free stream velocity times length over mu, or that equals U times L over mu. Okay, so basically, typically what you see in boundary layer theory is you see REX, you see things depending on REX, or the Reynolds number based on X, and things depending on the total length. Usually things depending on X are local values, and quantities depending on that are integrated over the entire length are typically based on REL. So that's just, it's not always that way, but just be very careful of it, is that some quantities are extremely local. For instance, this tau wall gives tau at any x location along the flat plate, but the drag basically integrates that tau wall over the entire length to find a net force. Okay, which is why the drag coefficient is based on based on a Reynolds number where the characteristic length is not x, it is L. Okay, and so that is it for this lecture.